The joint development team of Professor Shibata, the University of Tokyo, JEOL Limited and Monash University succeeded in directly observing an atomic magnetic field, the origin of magnets, magnetic force, for the first time in the world. The observation was conducted using the newly developed Magnetic Field-Free Atomic Resolution STEM, MARS-1. This team had already succeeded in observing the electric field inside atoms for the first time in 2012. However, since the magnetic fields in atoms are extremely weak compared with electric fields, the technology to observe the magnetic fields had been unexplored since the development of electron microscopes. This is an epoch-making achievement that will rewrite the history of microscope development. Electron microscopes have the highest spatial resolution among all currently used microscopes. However, in order to achieve ultra-high resolution so that atoms can be observed directly, we have to observe the sample by placing it in an extremely strong lens magnetic field. For this difficult problem, the team succeeded in developing a lens that has a completely new structure in 2019. Using this new lens, the team realized atomic observation of magnetic materials, which is not affected by the lens magnetic field. The team's next goal was to observe the magnetic fields of atoms, which are the origin of magnets, magnetic force, and they continued technological development to achieve the goal. This time, the joint development team took on the challenge of observing the magnetic fields of iron, Fe, atoms in a hematite crystal, alpha iron 3 oxide, by loading Mars with a newly developed high-sensitivity high-speed detector, and further using computer image processing technology. To observe the magnetic fields, they used the differential phase contrast, DPC, method, 2, at atomic resolution, which is an ultra-high-resolution local electromagnetic field measurement method using a scanning transmission electron microscope, STEM, 3, developed by Professor Shibata et al. The results directly demonstrated that iron atoms themselves are small magnets, atomic magnet. The results also clarified the origin of magnetism, antiferromagnetism, 4, exhibited by hematite at the atomic level. From the present research results, the observation on atomic magnetic field was demonstrated, and a method for observation of atomic magnetic fields was established. This method is expected to become a new measuring method in the future that will lead the research and development of various magnetic materials and devices such as magnets, steels, magnetic devices, magnetic memory, magnetic semiconductors, spintronics and topological materials. This research was conducted by the joint development team of Professor Naoya Shibata, Director of the Institute of Engineering Innovation, School of Engineering, the University of Tokyo, and Dr. Yuji Kono et al. Specialists of JEOL Limited, in collaboration with Monash University, Australia, under the Advanced Measurement and Analysis Systems Development, SENTAN, Japan Science and Technology Agency, JST. Terms: 1. Magnetic Field-Free Atomic Resolution STEM, MARS. An electron microscope is an instrument to directly observe the microstructure in a sample, where an electron beam is injected into the sample, and the electron beams transmitted and scattered by the sample are magnified using a magnetic phi. On the other hand, electron microscope is an instrument where this spatial resolution limit is exceeded by utilizing the wave nature of electrons. Therefore, it can be said that an electron microscope is an observation technology that applies the benefits of quantum mechanics in the most direct way. (3) Scanning transmission electron microscope, STEM, an instrument to directly observe the structure inside a sample. Story source. Materials provided by Japan Science and Technology Agency. Note: content may be edited for style and length. Journal reference: Yuji Kono, Takehito Seiki, Scott D. Findley, Yuichi Ikehara, Naoya Shibata. Visualization of the origin of magnetic forces by atomic resolution electron microscopy. Accelerating research and development on state-of-the-art materials such as magnets, semiconductors and quantum technology. Science Daily. Visualization of the origin of magnetic forces by atomic resolution electron microscopy. Accelerating research and development on state-of-the-art materials such as magnets, semiconductors and quantum technology. Visualization of the origin of magnetic forces by atomic resolution electron microscopy. Accelerating research and development on state-of-the-art materials such as magnets, semiconductors and quantum technology. Science Daily. https://ift tt JIFQ8RZ. Accessed February 24, 2022. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.